that we will define proper fraction, improper fraction, and so on beta. But before that beta, you put mute on your meeting so that you can get my voice clearly. Now we know that beta, this if we have a function that is of the form of this fx divided by gx, we call this, if it is tx beta, we call this tx, if it is in the form of fx gx, we call it beta a rational fraction, yeah, rational function. If and only if beta this gx is not equal to 0, if this gx is not equal to 0, then we say that this is a rational fraction. Now beta, we call this rational fraction as proper. We call this as proper rational fraction if the degree of this, we know that this fx and gx, they are the polynomials in x. If the degree of this fx is less than the degree of gx, degree of this fx is less than degree of gx, then we say beta this is proper. This is proper fraction. And if the degree of now this fx is greater than degree of fx, if it is greater than degree of gx, then we say it is improper fraction. Here you check beta. If we have fx divided by gx and the degree of this fx is greater than this gx, at that time beta, degree of this fx is greater than gx, at that time beta we can divide this fx by gx, and when we will divide this fx by gx, we will get some coefficient and we will also get a remainder. But this remainder must have degree less than this gx. So and this qx divided by rx, this so we can write this beta, this fx divided by gx at that time equals to you check here beta, we can write it cx, this qx no beta, we can write it better like this, fx is already, we can write it qx plus this rx divided by gx, because we know that beta this fx, when we divide this fx by gx, we know that by Euclid's dividend this fx is equal to gx into qx plus rx. So here this is same as this, because why beta, this gx will get multiplied by this, so it will be qx plus into gx plus this rx and divided by gx. The gx will get cancelled with this, we get f of x is equal to qx into gx plus rx, that is the Euclid division. So by Euclid division lemma we can write it as fx divided by gx is equal to this qx plus rx divided by gx. So if we have a rational, if we have this improper rational fraction, that fraction we can write as the sum of beta. You check here first, this is rx, and we know that beta the remainder has degree less than this, and when the degree of coefficient, when the degree of this denominator numerator is less than the numerator denominator, when the degree of numerator is less than the degree of denominator, at that time beta we say that this is proper fraction. So we have a improper fraction, but we are expressing that in terms of beta this qx plus proper fraction. So every improper fraction can be written as the sum of proper fraction and some polynomial. So I write this definition and you write this as remark, the last one. You write better. Yeah. A function of the form this fx divided with gx. Why this fx and gx are polynomials? Now gx is not equal to 0 is called a rational fraction. Rational fraction via fx and gx are polynomials next. So this is our first definition. Now you write proper rational fraction. Right bit of if in fx divided with gx is not equal to 0. If in fx into gx degree of fx is less than degree of fx is less than degree of gx, then fx divided by gx is called proper rational fraction. For example, beta, you can do this example as we have proper fraction when degree of fx is less than degree of gx. So I will take here x square plus 1 divided by x cube plus 3x plus 2. Now you write improper. Improper rational fraction. fx divided with gx is not equal to 0 is called improper rational fraction if degree of fx greater than degree of gx. And you write the note that I have already discussed with you, that is beta theory. Improper function can be written as, any improper function can be written as fx, जो भी improper function fx there can be written as beta this, for example, this beta fx divided by gx. When we are dividing this, we are getting quotient qx and this remainder rx, and then we are getting this fx divided by gx equals to, I have already given you it beta, yes, rx divided by gx plus qx. So this is can be written as this qx plus rx divided by gx, by this rx divided by gx is now proper. Right. Rx divided by gx is proper. Now beta, now we will go to our method beta, but before that beta, you have to take one thing in consideration, that is beta, this method is only applicable on proper fractions. So if we are going to apply this method, our function must be in the form of x divided by gx, but this fx we must have this degree less than this degree of gx, then we can apply this method. Otherwise, if we have a fraction that is non-proper, that is improper, then we have to convert that in terms of this qx plus rx divided by gx, and then we can apply the rule of one side. Now beta, if we have no proper fraction, for example beta f of x divided by g of x, we can write this proper fraction as beta this f of x plus a minus a divided by g of x. This will be further equal to beta f of x plus a divided by g of x minus a divided by g of x. Further we can write beta this f of x plus g divided by g of x. We can write this as minus a divided by g of x plus a divided by g of x plus 3a divided by g of, we can write like this beta, this proper fraction. So this I am expressing a proper fraction in terms of several fractions, but each fraction we are getting having denominator g of x, this denominator. These fractions beta, these fractions are called beta partial fractions. So beta, when we are so every proper fraction we can express that as a sum of rational fractions, and each rational fraction is called beta this partial fraction. We'll write its definition. Right, a proper function of fraction. So write rational fraction. A proper rational fraction. Can can be expressed as the sum of rational fractions, each having a simple factor this g of x. Each such fraction is called a partial fraction. This is my definition. You write now remark. Write down the remark. The remark is better. Remark में लिखो बेटा, the process of expressing f of x divided with gx as the sum of partial fraction is called resolution of fx. It's called resolution of fx into partial fraction. This is my remark. Now beta, we are going to discuss the method. These are the basic things you have to memorize, you have to take under consideration. Now we are going to define our method. What is method beta? The method is beta if you have a proper fraction, that proper fraction you have to convert into beta this as a sum of this rational fraction or as a sum of partial fraction. So this is for the rational fraction and this is for the proper fraction. But if you have an improper fraction, that fraction you have to convert as a sum of some function and improper fraction, and after that you can apply this method. So we are going to define the method that is based on this proper fraction. So what is my method? The method is beta, we have to convert the proper fraction into or we have to express the proper fraction as a sum of partial fractions. How we can express it? I am going to write it beta. If we have just beta, you write first one beta. If we have, I am going to give you simple rules how you can express your function as sum. So beta, if you have this f of x with g of x, if you have this improper fraction, how you can make it a resolution beta? If this g of x is equal to beta, if this is equal to beta, this x minus a, if it is the linear polynomial. What if our g of x is linear polynomial? But firstly, you have to take considering that this f of x divided with g of x, it is the proper fraction. That means the degree of this f of x is greater than the degree of this is less than the degree of this g x. So g of x is equal to x. If this is f of x minus a, then its resolution will be better. This you have to write it as a divided by x minus a. So if this, what that means beta, if you have this gx as this f of x divided by gx as f of x divided by x minus ay, this you have to write this fraction equals to beta this a divided by x minus a, and after that beta you have to find out by this equation the value of this a, and after that you can apply some math rule. Now this is my substitution is beta here. Second one beta, if you have gx, this denominator if you have equals to x minus a whole, so at that time beta you have to make its resolution as a divided by x minus a plus a b divided by x minus a का whole square. This is the resolution when our denominator is this. So, but beta sometimes the denominator should be in quadratic or in biquadratic, so on beta. We at that time beta we have to factorize the gx first, and we have to try to make it in beta the linear factors or the product of this quadratic or something, whatever we have to. So if this now beta gx is equal to x minus a ka whole, you have to write it beta as a divided by x minus a plus b divided by x minus a ka whole square, and then plus c divided by x minus a ka whole cube. For beta, if you have gx equals to now just quadratic. If we have the gx as quadratic, but this quadratic equations we cannot factorize, then at that time beta you have to make its resolution as a x plus b divided by ax square plus bx plus c to make this resolution. So fifth one, if you have now beta this gx equals to ax square plus bx plus c ka whole square, but this we cannot factorize this quadratic equation, then its the resolution is equal to beta. You have to write that these are the rules beta. These are the simple methods you can apply. Ax plus b divided by ax square plus bx plus c plus cx plus d divided by this is our the simple things that you have to remember. Now beta, we will try to solve some examples with the help of that you will understand this method beta. So in this method we have to make, first we have to check whether the function is proper or not. If the function is not proper, we have to convert that into proper function, and after that we have to make a resolution of that proper function as a sum of this rational function, and then we have to find out the values of these a, b and c, so on. So for example, if we have a function that is equal to then I will take a simple example that will be based on all the three things I have given you bit of. I will take I, if I have I equals to integral of x divided by x cube minus 1 x plus 1. So our this is push the f of x divided by g of x, that is equal to beta x divided by this x cube minus 1 x plus 1. This is our x cube and this is our function, but we have to first check whether this is we have to first check whether we can factorize this gx or not. If we cannot factorize, then we have to apply the method directly. If we can factorize, then we have to factorize first. So this x here, this is x plus 1, this is already factorized, but this x cube minus 1, we can factorize it, it will be equal to beta now x minus 1 into the factorization of this. You can check it beta, you can do by yourself, because you know that beta this x is equal to 1 is the root of this x cube minus 1. So we can divide this by x minus 1. When we will divide this x cube minus 1 by x cube x minus 1, we will get first x square, and it will be x cube minus x square, and then this one will get cancelled, this it will be plus, and it will come out as x square minus 1, and after that we can do the multiply of this by x, will be x square minus x. So it will minus, this will be plus, and this will get cancelled, this it will be x minus 1, and we will now do it's multiplying by this, and it will come out as x minus 1, this one minus, this one plus, and 0. So we can write this beta as x minus 1 into this is x square plus x plus 1, and then we have this x plus 1. This is our x and now beta we cannot factorize this because its factors will be that its roots will be on this complex field, but here we are dealing with rational number real field. So we will now put this x divided by x minus 1 x plus 1 x square plus x plus 1 is equal to, we know that if we are like this beta, we can write it a divided by what, x minus plus b divided by x plus 1. These are linears, we can write their fraction as this, and then this is quadratic, we know that that is equal to cx plus d divided by x square plus x plus 1. This now beta we can, it will be equal to, we will multiply this by this, I will get x is equal to a into x minus 1 x plus 1 x square plus x plus 1, and then b I will get here into x minus 1 into x square plus x. So one will get cancelled here. Plus 1, and then lastly we will get 6 plus d x square x minus 1 x plus 1. Now beta we have to compare the real coefficients, we have to compare the coefficients of real coefficients of like terms, and for, by that purpose beta we will get the values of this a, b, c and d. And after when we will get the values of this a, b and c, we can put them here, and we will get this function as the sum of partial fraction, or we can get the resolution of this function. So how we can get these values? You will compare first, you can put here the value of x as 1, this one will get 0, this will also get 0, but here it will be coefficient a. So when we will give the value of this x as 1, you will get the value of a at that time equals to, बाकी जो ये हैं और ये हैं वो 0 बन जाएंगे, लेकिन यहाँ पर बन जाएगा ये 1 plus 1 that is 2, and here 1 plus 1 plus 1 that is 3, 2, 3, 6, and that is a, and it will be here 1 divided by 6. 1 divided by 6. So yes, no, better here it is. When we get 1, it will be here 1 square, and then 1 plus 1 that is it. That will be 1 divided by 6. Yes, beta. and d you will get, when you will now put the value of this a as -1, you will get here minus, this one will get cancelled, this one will also get cancelled, here will be b, and it will be b at that time equals to -1 divided by 2 divided by 6, and then c will be, you can compare the quotients of x square here and here, you will get c as -1 divided by 3, and d you will get beta, when you will compare the quotient of x now, you will get d as 0. So now a is 1 divided by 6, b is -2 divided by 6, and 3 is 1. You can put here and you will get this thing equals to beta. This one you will get equals to x divided by x minus 1, x plus 1, x square plus x plus 1, you will get it equals to a. What is a here? That is 1 divided by 6, and then you will get 1 divided by x minus 1 minus b, that is 2 divided by 6, and here it is now 1 divided by x plus 1 plus cx plus d, that you will get cx, that is -1 divided by 3, and x, that is x plus d, that is 0, and divided by x square plus x plus 1. This is my resolution beta. Now I will integrate on both sides this. This is the method you have to follow for all the questions beta. Now here, when I will integrate on both sides, here it will be I, the integral that we need, and here it will be beta 1 divided by 6 integral of dx divided by x minus 1 minus 2 divided by 6 integral of dx divided by x plus 1. Here it will be -1 divided by 3 integral of x dx divided by x square plus x plus 1. Now beta, this we know that it is 1 divided by 6, and this one will become log of x minus 1 minus 2 divided by 6 log of x plus 1. Now we have this integral 1 divided by 3 x divided by x square plus x plus 1. Now we have to solve this integral. You can solve this by substitution method as well, and by the method of, but we know that for this we have, that's important to substitution. So ax plus b, we have to put that lambda times d by dx of derivative of this plus mu. So here you will do the same. You write this beta -1 divided by 6, and this will be 2x plus x minus we put this beta, this x, put this x is equal to beta, what is there, lambda times d by dx of this x square, this x square plus x plus 1 plus mu. So it will be here x is equal to, what is here, lambda d by dx of this, what is that, 2x plus 1 plus mu. Compare the quotients of beta here. X is equal to 2 lambda x plus lambda plus mu. Compare the quotients like that, you will get 2 lambda is equal to 1, lambda is equal to lambda plus mu is equal to 0. So you will get here lambda is equal to minus 1 divided by this 1 divided by 2, and mu you will get that lambda and this, that will be minus 1 divided by 2. Hence you got beta lambda is equal to this and mu is equal to this. So here it will be now, our substitution will be here. Yes, x is equal to lambda, that is 1 divided by 2, and d by dx of this, that is 2x plus 1, 2x plus 1, and then plus mu, that is minus 1 divided by 2. We will substitute this to our integral and we will get the solution. Then it will be I is equal to 1 divided by 6 log of x minus 1 minus 2 divided by 6 log of x plus 1 minus this 1 divided by 2, 1 divided by 2. We will make it factorize here. So we will get beta here, this. That's 1 divided by 6 and then 2x plus 1 minus 1 divided by this thing, x square plus x plus 1. Now you will put this to 0. When you will put this to 0, to this t, you will get 2x plus 1 dx is equal to dt, and you will get this integral after this. But after that you have 1 plus 1 divided by 6 integral of dx divided by x square plus x plus 1. This is now easy beta because you know that this integral can be solved by the method of completing the square. You have to convert this in terms of square of 2. So, and then you can get the solution. This was the first example, and you have to follow this method, find the solution of all the, you have to convert first your fraction into this sum of partial fraction, and after that you have to find out the values of the constants a, b and c, then you have to integrate on both sides. This was my final. Now beta we will, tomorrow it will be our great concept, that is definite integral. And for your kind information beta, this is the beautiful now. This is the beautiful thing that we have to discuss in integration beta, because we are going to now take this integration to the area of curve. We will compare this one now. We will make this definite integral as beautiful as it will help us to find out the area under a curve. So we are going to define it tomorrow.